All right, so section 4.1, as it says up there, we're going to talk about probability distribution functions for a discrete random variable, whatever the heck that means. We're going to talk about that. Okay. First of all, a discrete probability distribution function has to have two characteristics. If it is missing one of these, then this does not work with what we're doing here. Okay. First of all, each individual probability has to be between 0 and 1. Okay, or if you change it to percentages, between 0% and 100%. It can be 0, it can be 100, okay, but each one of them has to be within there. So if you do some kind of statistical analysis and one of them is 120%, then we're not talking about this, okay? The other part is when you add them all together, the sum of the probabilities is 1 if they're all decimals or fractions, or 100%. Okay, so just be aware of that. Those are the only two characteristics of them. So they all have to individually be between 0 and 100%, and they have to add up to 100%. Okay, so if we look at this first one here, and this might just be one that you look at here, all right? We've got a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. Okay, X is the number of times a patient rings the nurse during a 12-hour shift. And then P of X is the probability of that happening. Okay. Why is this a discrete probability distribution function? So if we look at this, here's our probabilities for each one of these situations. All right, what are the two reasons why this is a discrete probability distribution function? They are all between 0 and 1, yeah? Do they? Make sure. Yeah, they do. Okay. So if you add up all of these, and these end up adding up to 50 out of 50. So they add to 1. All right. You're going to be asked questions just as simple as that. Okay. Some of the questions in your homework are going to be, all right, you're going to get a set of data points like this. What's wrong with this? What doesn't make this work? Okay, so you're really going to have to look at it. Okay, for one of them, it actually took me quite a while to figure out what was wrong with it. Okay, so just that's really what you're looking for. All of them have to be between 0 and 1, which they all are here, and they have to add up to exactly 1. All right, any questions there? All right, we'll go on to the next one here. This one you'll probably want to write down because there's a little bit more math to it. Eli, you can always get it later. It's 2 lines that you missed. All right, so get this stuff copied down. This would be a more traditional question that you would get asked based off of this stuff. Jacob's first class in like 2 weeks, and he's taking even better notes today than he normally does.
I wrote down 3 classes a week, 3 days, 80%, 215, 1 day, 4.
I know. I said better notes than normal. What are you getting at, Jacob? Huh? What are you getting at?
You didn't go that long.
All right, so we've got 3 questions to answer up here. All right, based on that data, Nancy has, as Jacob said, Nancy has 3 classes, or has classes 3 days a week. She attends classes 3 days a week, 80% of the time, 2 days, 15% of the time, 1 day, 4% of the time, and no days, 1% of the time. Suppose 1 week is randomly selected. All right, first thing we got to figure out, what does X stand for? What do you think? What is the thing that is changing here? How many classes she attends, right? And this would be per week. All right, so X takes on what values then? What are the possible answers for this? Right. Okay, can be in any order. I just went from least to greatest. All right, and then letter C says, suppose 1 week is randomly chosen. Construct a probability distribution table. The table should have 2 columns labeled X and P of X. All right, so our X values, as we just said, were 0, 1, 2, and 3. Okay. When you do this, technically you can go in any order you want, but you do want to make it the most legible. Okay. So normally we go from least to greatest and something like that. All right. And then we just put the probabilities that go along with it. All right. So 1%, you can either put 1% in there or you can change it to a decimal. It doesn't matter which way you go here. All right. I'm going to leave them as percentages. You do have to put the percentage in there then. And 80%. All right, and there's our probability distribution table. That's all it is. Okay, we're going to use this in the next lesson to be able to answer more specific questions with this. All right. All right, what does the P of X column add up to? Yep, 100%. All right, which is the whole point of this lesson, right? They've got to add up to 100%. So this would be another one where each one of them is between 0 and 1, and it adds up to 100%. So it would be what we're talking about here. All right, any questions there? Nice and short. This one's a little bit longer. This one takes a little bit more math ability here. So 4.2, we're talking about the mean or expected value and standard deviation. Right, so as it says up there, the expected value is very, very similar to the mean. All right, it is not always exactly what the mean is. All right, but it is what you should expect as your average. So for example, as I said down below there, if you were to toss a coin 100,000 times, what is the expected value of getting ahead after those would be, it wouldn't necessarily have to be exactly 50,000 times, but it should be very, very close to it. Okay, one variable that you are going to see that is new is this variable here. It looks like a U with a tail on the front of it. Okay, how we pronounce that is mu. Yeah, so mu is what you're going to hear. So mu is the expected value. All right. So go ahead and get that copied down, and then we'll do some examples on what we're talking about with this stuff. And then after a couple slides, we'll talk about a little gambling to see probability of actually winning money in certain events. Maxwell passing notes during class, huh?
Would you like to see it?
Would it keep him eligible if I did see it?
It says, no, it's not bad. It's just a voice thing. Silly voice.
All right, so we've got a situation here, okay? A men's soccer team plays soccer 0, 1, or 2 days a week. Probability they play 0 days is 0.2, 1 day is 0.5, and 2 days is 0.3. We want to find the expected value of the number of days per week the men's soccer team plays soccer. And then we're going to figure out what the standard deviation is of this also. So get this written down. These are the sorts of problems you're going to be doing homework-wise. All right, so even though it does say standard deviation here, technically you can do standard deviation the way that you guys have been taught in the past. This is just another way to do it. All right, for some of this, we can start filling in right away. All right, we know that the X is going to stand for the number of days per week that they play. So we know our X values are going to be 0, 1, and 2 here. All right. We also are given what the probabilities are here. So this probability would be 0.2 for 0, 0.5 for 1, and 0.3 for 2. Okay. Once again, this follows what we were talking about in the last lesson because each one of the probabilities are between 0 and 1. And if you add these together, it adds up to 1. Okay. Now, to find our expected value here, what we're going to do is we're going to take 0 times 0.2 to get a 0 here, 1 times 0.5 to get a 0.5, and 2 times 0.3 to get a 0.6. Okay, now we need each one of those values to come up with the expected value of the number of days. How we find that expected value is we just add these three together. All right, so our expected value of how many days per week that they're going to play is 1.1. All right, and then what we can do with that, so this is our first answer. Find the expected value. That's going to be 1.1 days per week. Then what we can do with that is we can use that to find our standard deviation here. All right. And all we do is we're going to plug in what we know for each one of the letters in our equation here. So we're going to go 0 minus 1.1. That whole thing is squared. And then we're going to multiply it by 0.2. And we get 0.242. We do the same thing for the other one. So we're going to go 1 minus 1.1 squared and multiply that by 0.5. We get 0.005. And then for the last one, we go 2 minus 1.1 squared times 0.6. I'm sorry, 0.3. And we get 0.243 here. Okay. Now, we have to use these numbers to be able to get our standard deviation. All right, your first step for this is we need to add all three of those together. And we get an answer of 0.49. All right, and then our very last step to find standard deviation, we just take the square root of that. So we would get a standard deviation of 0.7. All right, now with what we're going to do on Thursday, we're going to use those standard deviations to be able to come up with different values that we're going to use for stuff. Okay, we're just trying to get this down for now. All right, now, standard deviation equation that you've been taught in the past, it's all in there. The only difference with this standard deviation equation is we have probabilities thrown in there also. Okay, so how do we use those probabilities to be able to come up with that, that's going to be this equation right here. Okay, so lots of steps to it. Okay, but there is a logical progression there. And really, these steps that we're going through is not any different than the standard deviation equation that you already know. All right, any questions on this one before we move on? It only happens when, like, what did you, how did you get it in your calculator? What did you do? You had the two different columns. I don't know if that's always, if that always works or not. I'd have to look into it. And I did all this stuff without calculator last night, so. All right, so this one here. All right. You're going to play a game of chance in which 5 numbers are chosen, 0 through 9. A computer randomly selects those 5 numbers, 0 to 9, with replacements. So once the first one is picked, you could pick it again. You pay $2 to play. If you win by getting all 5 numbers in the right order, you would win $100,000. Over the long term, what is your expected profit of playing the game? Okay, so what we can do here is we can do kind of the same concept here. All right, now the very first thing that you have to figure out is what is the probability of winning? How are you going to figure that out? What's the probability of getting the first number correct? 1 out of 10, right? It is replacing it. So what's the probability of the second one being right? And the third one, and the fourth one, and the fifth one. All right, does that make sense? If you change that, if you multiply all that together, I'm going to change it to a decimal. That's what we would get. All right. The other thing that we're also going to need for this is the probability of losing. All right. Well, for this, you can either win or lose, right? So if the probability of winning is this, we can just go 1 minus that to get the probability of losing, which would be 5 nines there. All right, now with that, what we're going to do is we are going to set up a distribution table to be able to figure out what our expected value is going to be. All right, well, for this, as we just said, you are either going to win or you're going to lose. All right, now we are still going to have our X value. What do you think our X values are going to be here? What is the amount that's going into this game that is going to change? The numbers that are going to change is how much you win, right? Or how much you lose. So if you win, you're going to win $100,000 here. If you're going to lose, we're going to have -2. Okay, that is what is changing for this, is the expected profit at the end. All right, now for this, we also have a probability of finding each one of those, and we just figured that out. Probability of winning would be 0.00001. Probability of losing would be this other one here. And then to find our expected profit for this, we would just multiply those. All right, so when we multiply these two together, we get a positive 1. When we multiply our bottom two together, we get a negative 1.49 and an 8. To find your expected profit of this, we would add these two together, and we would get a negative 0.99998. Okay, now what does that mean in real terms? Okay, you are expected to lose $1 every time you play, because what is this talking about? This is talking about money here. Okay, this is not a percentage here. This is talking about money. So you would be expected to lose $1 every time you play. All right, so for those of you who are turning 18 or who have already turned 18, you could definitely go start to play, say, like the Powerball. Okay, and you could figure out exactly what's going on there with that. Okay, and you would figure out, the reason why they do this stuff is because for most people, they're going to lose money every single time they play. Okay. All right, any questions with what we're doing there? All right, let's go to another one. Suppose you're playing a game, you are told that it's a biased coin. You play each game by only tossing the coin once. The probability of getting a head is 2/3. Probability of getting a tail is 1/3. If you toss a head, you toss the coin, you get a head, you have to pay $6. But if you toss the coin, you get a tail, you win $10. If you play this game many times, will you come out ahead? So when you're asked a question like this, they're asking you to find the expected value. Okay, so we're going to do kind of the same concept here. We need to find what is our x value, what is our p of x, and then we've got to find x times p of x. What is, in this situation, what is changing here? The money, yeah? All right, so if you win, you're going to have a positive 10, right? If you lose, it's going to be a negative 6. That's what's changing here. We know the probabilities. We know probability of winning is 1/3. We know the probability of losing is 2/3. Then we just have to multiply those together. So 10 times 1/3 would be 10/3. Negative 6 times 2/3. Negative 12/3. To get your expected value, we're just going to add those two together. And we see that every time you play, you would lose, on average, 67 cents. Okay, so on average, will you come out ahead in this game? No. That is technically true. Yes, you're right, Max. Okay, so now, for those people that this is all their job is, they go to the casinos, they play these games, what they figure out to be good at this, they figure out what the expected value is. I'm good. And they're trying to minimize this number. Copy down this next situation, please. Now, this one is going to be a little bit different because we have two die going at the same time. All right, and that means that our sample space is going to be very different here. Okay, so that's why we're going through this problem. And this one will be the last one of the day. So we're almost done here. Now, for some of these problems, like what we're going to see with this one, our sample space is going to get really big here. All right, when your sample space gets even on the bigger side and it's a little bit more complicated sample space, it's almost always better to list them out. So for example, what we know for sure is if we toss the first dice, we would get answers of potentially 1 through 6, right? And then if we do the second die, we would get anything between 1 and 6 also. All right, so, and I'm not saying you have to do this for every single one, but sometimes it's important to be able to see, all right, if I get a 1 on the first one, I could have 1, 1, 1, 2, and so on, 1 through 6 here. All right, and then we do the same thing for 2. All right, and like I said, I know this is super tedious, but it can help us get the correct probabilities later on here. So don't be afraid to list out all of these different possibilities. All right, so there's all of our different possibilities there. How many total do we have there? 36. All right, so we're going to need to know that number in just a little bit here. All right, now X stands for the number of faces that show an even number. So in this situation, what are our possible X values? The number of faces that show an even number. It's not 2, 4, 6. Good try, Max. Well, one of them's right. 2 is right.
No.
Okay, apparently 2 is stuck there. All right, what else is a possible answer here? 0 is also an answer, yes. And what else? I'll explain in just a minute. A 1. Okay, now, X stands for the number of faces that show an even number. You are rolling 2 die, all right? The maximum number of even numbers that you could have would be 2. The minimum would be 0, and so on, okay? Now, there we go. Let me spread these out a little bit more, so because our numbers get a little bit bigger here. All right, now what we have to do is we have to figure out the probability of having neither one of the die being even. So we count these up. This one, neither one of them's even. 2, 3. These would all have at least one even. So 4, 5, 6, 7, 8, 9. So probability of having 0 even numbers would be 9 out of 36. Now you can change that to a decimal if you want, or a percentage if you want. It's up to you. Okay? Then we go through and we do the same thing for a 1. All right? And if we were to count those up, we'd have 1, 2, 3, 4, 5, 6, and we'd keep going, and we would get 18 of them. And then for our last one, we count up where both of them are even. So we would have 3 in the 2s, 3 in the 4s, and 3 in the 6s. So that'd be 9 out of 36. Now, what should happen when you do these every single time is just like what we talked about earlier. These probabilities should always be between 0 and 1, and they should add up to exactly 1. If they don't, chances are you missed something. Okay, so go back and check it. All right, we do get, if we add these 3 together, we do get 36 out of 36 here. Okay, so then to find our x times p of x, we just multiply those two together. So we get a 0 here. We get 0.5. And we get 0.5 here also. So then to calculate our expected value, we just add those together. So our expected value, we are going to get 1 even number on average for as many times as we roll these dice. Okay, then to find the standard deviation, we just plug stuff in. All right, so we've got 0 minus 1 squared times our probability, which would be 9 out of 36. Then we do the same thing for the other ones. And then remember, to find standard deviation, we have to add those together. So we get a 0.5, and then we take the square root, which is 0.707. Or technically, since we're going 1 decimal place past, 0.71. All right. Any questions there? All right, like I said, with what we're doing on Thursday, we're going to use this information to be able to do more complex stuff here. So we're just trying to start the process here. All right. Homework. And I expect you guys to get rolling on this right away, or previous homework assignments if they are not done. 1 through 36, okay? It is very, very straightforward here. Lots of the questions